When standing on a quiet street, the ground feels solid and unmoving. But that sense of stability is an illusion, because just a few hundred kilometers below your feet, the Earth behaves like a slow boiling ocean, a hidden world of molten rock that never fully cooled, a world we are only now beginning to understand. And it leads to a shocking question. What if Earth is not a solid planet at all? What if, deep beneath us, the remains of an ancient global magma ocean still exist? For decades, this idea seemed like science fiction, but new seismic studies offered evidence that the early Earth's molten past may still be alive inside the planet today. And to understand this hidden ocean, we must travel back in time, 4.5 billion years ago. Earth did not begin as a blue world with oceans and continents. It started as a hell planet, a swirling mass of molten rock formed from violent collisions of cosmic debris. The most important of these collisions happened around 4.5 billion years ago, when a Mars-sized object, often called Theia, slammed into Earth. According to NASA's planetary formation models, this single event released enough energy to melt the entire planet's surface. For millions of years, Earth was covered by a global ocean of magma hundreds of kilometers deep. Scientists call this the magma ocean phase. During this era, the atmosphere was toxic. The sky glowed red with volcanic gases, and the entire surface churned like a slow-motion storm of liquid rock. As the planet cooled, the upper layer solidified, continents formed, oceans appeared, and life eventually emerged. But not all of that magma ocean disappeared. Some of it sank deep into the planet and became trapped, locked beneath the mantle, preserved for billions of years. And only recently have scientists begun to detect signs of its existence. So how do we know this hidden world might still be there? It comes down to earthquakes. Every time the Earth shakes, seismic waves travel through its layers. They move differently depending on the materials they pass through. In 2023, researchers studying deep quakes beneath the Pacific and Africa found something that didn't match any known model. They detected vast regions where seismic waves slowed dramatically, almost as if the waves were traveling through hot, partially molten rock. These regions are now known as ULVZs, or ultra-low velocity zones. Some of them stretch for thousands of kilometers. The most famous two are beneath the Pacific Ocean and beneath Africa. In early 2024, teams from MIT and Caltech published papers suggesting these ULVZs may contain material left over from the early magma ocean, material so ancient it predates the moon. They concluded this after studying the chemical fingerprints of volcanic rocks that originate deep in the mantle. These rocks contain isotopes that formed only during Earth's earliest molten period. This means the magma ocean didn't vanish, it simply moved inward, buried far below the surface, locked away beneath the mantle. Which brings us to a surprising truth. Earth is not a solid planet, not in any simple way. The top layer, the crust, is solid, but the mantle beneath is not. It behaves like a thick, viscous fluid, slow, but constantly moving. This slow movement drives everything we see on the surface: earthquakes, volcanic eruptions, mountain formation, even the drifting of continents. If the mantle is the engine of the planet, this ancient magma ocean may be its fuel tank. And now scientists are asking a bold question. Does this ancient material still influence life on the surface today? The answer might be yes. Start with volcanoes. Some of the most powerful volcanic hotspots on Earth, like Hawaii and Iceland, may be connected to plumes rising directly from these deep molten reservoirs. According to USGS studies, these plumes could be tapping into primordial material billions of years old. This could explain why lava from certain hotspots has chemical signatures unlike any other magma on Earth. Then there is continental movement. The African continent, for example, is slowly splitting apart. Scientists call this the East African Rift. Satellite data from the European Space Agency shows the region stretching by a few millimeters every year. Why is this happening? One theory points to the ultra-low velocity zones beneath Africa. If this molten region is hotter or more buoyant than the surrounding mantle, it could be pushing upward, reshaping the surface. It's like heat boiling beneath a pot of soup. Eventually, the pressure forces the top layer to crack. But perhaps the biggest question is how this ancient magma ocean survived for billions of years. With so much heat, why didn't it cool? The answer lies in pressure. The deeper you go inside Earth, the more intense the pressure becomes. At certain depths, the pressure is so extreme that rock cannot behave like a normal solid. It begins to soften and behave like thick honey. Even at temperatures of thousands of degrees, it doesn't fully melt. Instead, it enters a strange hybrid state. This is why scientists say Earth is not solid. It is layered, dynamic, and alive. And now we come to the most fascinating part of this story. The magma ocean beneath our feet may not be a single ocean at all. Some studies suggest it could be a network, a patchwork of ancient molten reservoirs spread across the deep mantle, each shaped by billions of years of convection, pressure, and chemical separation. Imagine giant lakes of molten rock sitting deep below the crust, some calm, some boiling, some rising slowly towards the surface, others sinking deeper, carrying ancient minerals into the core mantle boundary. This underground circulation may even power the planet's magnetic field. The core generates the field, but the mantle transfers heat in patterns that influence the core's movement. If the flow of heat changes, the magnetic field changes. It has flipped many times in Earth's history. According to research from the University of Wisconsin, these reversals may be linked to variations within deep mantle structures that include ultra-low velocity zones. So the ancient magma ocean might be shaping our magnetic shield even today. All of this raises an unsettling question. Could these deep molten regions pose any danger? Well, not directly, because they're far too deep to melt the surface. But indirectly, they influence volcanic activity. They affect where new crust forms. They shape where tectonic plates collide. And in the long term, they may contribute to supervolcanic eruptions. Yellowstone, for example, is powered by a deep plume, not one directly connected to a ULVZs, but similar in behavior. According to the USGS, its magma chamber feeds from a mantle plume that may originate hundreds of kilometers beneath the surface. If a ULVZ-fed plume rises in the future, it could create new volcanic hotspots, reshape continents, or trigger new rift zones. This is the natural evolution of the planet. Earth is still cooling. The ancient magma ocean is part of that slow geological heartbeat. And here is the biggest irony. The solid ground we stand on exists because of molten rock. We live on a thin shell, a fragile crust, a surface so thin that in proportion, it's like the skin of an apple. Everything beneath is moving.